lesson is on curvature and normal vectors. And there is an awful lot to say about section 13.9. So much so that I really think you guys will probably be working on this section for about a week. That's kind of what I'm picturing. Okay. If you get all the homework done by next class, awesome. But if you don't feel you're behind necessarily. As a matter of fact, when you look at what I'm, assigning over the next few days, okay, you'll see that, yeah, I picked out a lot of problems for you guys to try, okay, for this section on curvature and normal vectors. I feel like, in some ways, this is a real nice way to end our work on vector calculus. And then you'll notice that before we take an exam, I'm going to have us get into the beginning of Chapter 14. Chapter 14 is not vector calculus, although it is the world of R3, three-dimensional space. Okay? And so 14.1, depending on who your Calc 2 instructor was, you may have already seen a little bit of talking about, because we've done lines here in Calc 3, remember? We had the parametric equation of a line. Well, the equation of a plane is even simpler. And so you may have done some of that, but you haven't done other surfaces, okay? And so you'll notice that Wednesday I have two sections I'd like you to work on, but no homework. The only thing I'm going to have you do is just the quick check exercises. There's plenty. I think they gave you 10 for section 1 and 9 for section 2. I said if you do all that, that's enough, okay? And plus, I think that gives us extra time to spend more time in chapter 13. Okay? And then we have one other section that I'll put on exam 1. Exam 1 will cover basically what we've covered up to next Tuesday. When you start doing limits and continuity, I think there are some exercises that are worth doing. And that's calculus then at that point again. So we start talking about limits. Question? Are they? By 3 days. Well, then let's fix that. Right, because today's the right. So you can't. And last Wednesday was not the 28th either. And no one said anything, right? Oh, here's the problem. I have 10 days between Martin Luther King and the following week, right? So at that point, well, let's just put it this way. I don't plan on fixing the entire calendar in front of you. But today's what, the 30th, huh, guys? I'll at least fix that much. And then February 1st would be Wednesday. So it looks like, okay, so your first exam is scheduled for Wednesday, February 8th, which means this must be the 6th. Is that better? Okay. And then I'll fix the rest of the days before posting this on Blackboard. Okay, cool. Thank you. Other questions or comments? So that's kind of where we're headed. I'll talk more about exam 1 maybe next time as we start, you'll be a week away from it. But today there's enough to talk about just in looking at this section on curvature and normal vectors. Oh yeah, so the Witwack, right? So I asked you guys as I was setting up for today, okay, what can you say about vector t and vector n? What are these things, right? That's really part of the discussion. What'd you guys come up with? Little facts that I should list for the television audience at home. Go ahead, Ted. Okay, so capital T here. Capital T does stand for the unit tangent vector. Why did I say unit? What does that mean? Magnitude 1, right. And so the way to get that, right, we know that if you want to get a line tangent to a curve or a vector tangent to a curve in Calc 3, what we've been doing is we've been doing this, r prime of t, right? So in general, for you guys, r of t has been my vector valued function. R prime of t, just like it did in Calc 1, gives me the tangent vector. And so if I'm thinking of this as position, then this is velocity, is a nice way to say it. But what we did also is we said we want it to be a unit vector, so we divide by the magnitude of r prime, and then that's the definition of your unit tangent vector, right? And then n stands for what? Normal vector. What does that mean? This is my unit normal vector. Anyone? Well, at least we know what it means. And you don't have to know because I'm supposed to cover that today, right? I'm supposed to cover curvature, which I'm extremely excited about covering, and normal vectors, which I will talk about and show you some pictures and hopefully get you to understand. So let's look at pictures. Pictures say 1,000 words, right? So let's look in the book. And so, well, yeah, there's this whole curvature. Curvature measures how fast a curve turns at a point. The normal vector describes the direction in which a curve turns. And then they talk about something else called the binormal vector, which I'll get to in a moment. But here's your definition. Principal unit normal vector. Whoa. Okay, well, let's jot some of this down and see what we understand and what we don't. So I guess I want to go ahead and write down what n equals. How do you read that? When I write dt vector ds, and then you'll notice that the rest of the formula was this. But you could probably explain why you have this piece of the formula also. Why do we have the bottom piece of the formula? All that does, and it's interesting to use the word normalize, because that is right. We want to make it a unit vector. The fact that it's a unit says, okay, divide by the magnitude, and that way the length will always be 1, right? Okay. Now, what is this? How do you read that? That's Leibniz notation. It's a derivative. That's right. That's exactly right. Change in the tangent vector with respect to the arc length. You know, it's interesting because I just wrote t. I could have written that t is a function of a parameter t, right? Remember, we're visualizing parameter as speed. We showed you last time that we met how I can change parameter and make us go through a curve more quickly or more slowly or at different rates. And then we also showed you that, in fact, sometimes you can think of the arc length as the right speed to go. Because we studied arc length last time. So you can switch the role of t and s, and when you do that, you can actually take this derivative, the derivative of t with respect to s. And if you do that, and then divide by the magnitude, that's the normal vector. That's the normal vector somehow. So maybe I'll say one more thing here. I said pictures and I haven't shown them yet. Let's do that. No? Here. Here's a picture. Good. Let's see what it looks like. They're showing me a curve in space, right? Here's my tangent vector. Here's my normal vector. Let me move this back a little bit so I can take a look. Okay. So as I travel, you can see that my normal vector seems to be changing direction while my tangent vector might be changing a little bit of direction, but not very much, right? And then when I get to this part of the roller coaster, what's going to happen? The tangent vector now points down, right? This is my moment, right? Where's the normal vector pointing? The normal vector, well, it's moving different places, isn't it? Now the normal vector is kind of pointing maybe to the right, and then it ends up pointing up. Both of these are unit vectors. And again, what's the relationship between t and n? N is perpendicular to t, or orthogonal is another word we like to use with vectors. And that means the same thing in R3.
Is it always pointing to the inside of the curve as opposed to the outside?
Yeah, so you guys are right on to the two big facts that they want to get across right above. Properties. T and n are orthogonal for all points of the curve. And the normal vector points to the inside of the curve in the direction the curve is turning. That's exactly right. Because if you think about it, when I'm in R3, okay, I have a vector. You know, in R2, if I say, hey, draw me something perpendicular at the end of that vector, well, I'm kind of stuck. I do this. But in the world of R3, there's actually infinitely many normal vectors that are all perpendicular to a given vector, right? So when I say n, I want to talk about which one am I talking about. And it has everything to do with the curve itself. You're right. And the way you guys described it, pointing where the curve is going, that's what the normal vector does for us. Okay? So those are good things to understand. Yeah?
So when you talk about the normal vector being the change in the tangent vector with respect to the arc length,
yes.
Are you talking about the change of position? Because we're not talking about magnitude, we're only talking about position.
And that's a very good point, because we have defined these things to be unit vectors. And you might ask, why? Why do we want unit vectors? And here's why. Because that's exactly what we want to measure. We want to measure change in direction. You guys, when I'm driving a car, I can accelerate in two different ways. Because what does acceleration mean? Accelerate means I am changing the velocity. One way to do it is to change the speed, and we've talked about that already. But the other way to do it, to change the velocity, would be to change its direction. Now in a car, how do you do that? You use a steering wheel, right? And that changes the direct, well, sometimes, not today on the ice, but in general, that'll change the direction you're heading. And so when we want to talk about dt ds here, the nice thing is that, like you said, Kathy, this is a unit vector. So remember, when if I ask you guys, what's the magnitude of t, that's always 1. Whereas if I say, what's the magnitude of just r prime of t, well, whatever that is, we call that the speed. So I don't want the speed to change. And actually, we can prove now, actually we already have proven, once I kind of remind you, the first part, that t and n are always orthogonal, okay? So here it is. T and n must be orthogonal. And why is that? Well, because there was this proof we did where we said r and r prime, vector r and vector r prime are orthogonal if, and I think the wording we used was, if r is moving at a constant speed. Is that what we said? I think we said something like that. I'll show you guys the argument. I mean, it's basically here. No. t has constant length, n has constant length. Yeah, but it was problem 13.8 here. I know. Yeah, back when we studied motion in space, we studied straight line and circular motion. Let me find it and then zoom in. Yeah, we had circular motion, straight line motion, and here it is. Yeah, motion with a constant speed. I'll make it a little bigger so you guys can see the argument. We wrote this out in class on the notes. I know we did. Uh-oh, don't do that to me. So you'll find that you have basically you have this proof worked out in your notes from last time, I think, or maybe 2 times ago, where we did the derivative of r dot r. We used our product rule and r prime showed up. And so basically when you get that r prime and r dot to 0, what does that mean? It means that r prime and r have to be perpendicular. Well, if r prime and r are perpendicular, you see t is just a vector, and n is the derivative of that. And again, since we have unit length, the speeds are constant. So almost the exact same argument gives you this fact that I just wrote in pink. Okay? So yeah, they'll always be orthogonal. And so that's kind of nice to have. Now, moving on, just to show you maybe one more little thing we can do here. Oh yeah, so I guess I have to restart that software at some point. But we're going to have the binormal vector, okay? And then we get what you might call a 3-frame. So your book says, okay, we're going to take the cross product, okay? So t cross n. What does that mean? Well, does this give me a vector or a scalar when I cross product 2 vectors? It gives me another vector, okay? So this yields a third vector orthogonal to the first 2. And we call this third vector the binormal vector. I want to write capital B with an arrow over it, but I want to make sure, is that what your book does? Yep, okay. So B is equal to T cross N. And again, I'm going to show you guys some pictures again once I start that software up. But again, if you have some curve in space, right, you're going to have T is the tangent vector, which, you know, think of it as, you know, your derivative. But then if you take dt ds, somehow n is my normal vector, and then a cross product to each of those 2 would be my binormal vector. And so you can think of this as, this is interesting, I think. Here, I like to show this picture. You see that? Yeah, my hand. So what is this? This is what is sometimes called a 3-frame. I've also heard it called a Frenet frame. This is a name that you might hear in the subject known as differential geometry, where people study kind of the limits and the calculus behavior of geometric curves. And in order to do that, sometimes it's helpful to have a coordinate system. And this Frenet frame, this little tiny 3 perpendicular vectors, gives you an XYZ system where you can study things that happen very locally. Now, I think I'm done with binormal vectors at that point, other than to show one more picture. And it kind of shows you how the binormal vector also, this represents what is called torsion or twisting of the curve. And but I'm going to need my software back to show you a nice picture of that, because again, a static thing doesn't show you. You almost have to see it moving. So if you've ridden some of the new rides at Cedar Point, boy, that's a great way to understand what we're really talking about when we talk about torsion. It's like the Raptor. Well, we can move on from there. Okay, so that's maybe the easier part of the section, is understanding what normal vectors are. I skipped curvature. I want to go back to it. And there's a lot of really nice opportunity for us when we study curvature. It's funny because if you just looked at the homework problems, I think you'd be missing out on what's there. And so I want to take you into the text itself. And that was part of the reason I said, well, let me give the wit whack this morning and go from there. Okay, so I have the sections that we want to cover. We talked about normal vector. We talked about binormal vector and torsion a little bit. But curvature is where I want to go next. And it's interesting because, well, how do they define it? Here's some discussion like what I said earlier, but here is your unit vector t. And then they say, okay, let's look at this picture. This is some nice stuff going on here. How quickly does t change as we move along the curve? If a small increment in arc length results in a large direction. So let's see the picture here, because I think it's better than the text. Watch. I have a tiny bit of arc length here. Actually, let me make that bigger. Oh, I see. So here. We need some curve. Here's some curve. S. S is the length. Actually, let's go the full gamut here, right? So here's a big curve, and notice it's quite curvy, you might say, right? So this particular curve has lots of curvature. And let's make delta S really small. Now, what is delta S? Delta S is measuring the distance between, say, this point and that point. Oh, now I see why they didn't want so much arc length, because they want to, here, you get a better picture of it maybe over here. So when delta S is big, you'll notice that there is a difference between T of S and T of S plus delta S. I think that I can do a little better than what they're doing here on my paper, so let me pull it back out for you. Here. Kind of recreate what they're trying to say there. Here is my curve, and I'll draw it like they did. They drew it kind of like that, right? And you'll notice we're traveling counterclockwise, right? So let me even orient the curve, because that's going to be important that you know which way you're traveling, okay? So I can compute T of T. And let's suppose that capital T, my unit vector, is, does that look tangent? I'm trying, okay? And then what I'll do is I'll move a little bit farther. I'll wait just a little bit longer, right? Oh, it's coming back. T of T plus delta T. Oh, wait a minute. For this to work out right, we're much better if we actually choose a particular parameter. We want to use arc length. So let's say that this blue actually represents the curve parameterized by arc length S. And therefore, the green is going to be T of S plus delta S, right? So I move a little bit farther along the curve, and I notice, is it pointed the same direction or a different direction? It's a different direction, right? Well, how much different is it? Well, I don't know. I mean, I guess T of s plus delta s is this green one, and T of s is the blue one. And now what I could do is I could imagine computing this. T of s plus delta s minus T of s. And of course, these are all vectors. I'm going to forget those arrows sometimes, guys. All right, so how do you subtract two vectors? Well, I know how to add two vectors. If I wanted to add the vectors, what I would do is I would take, remember I can reposition these things wherever, so I would take that blue vector that I had, remember it? And I would take the green vector that I had and I would give them the same endpoint, correct? And so this one's pointed more like that. Are you with me? Or maybe I would go tip to tail, but basically the sum would be if you take this diagonal. Well, the difference of those two vectors would be this diagonal. See that pink? That is this difference. Well, what we're going to do when we start talking about curvature is we're going to do two things that we've done before in calculus. Because as soon as you write this, does this look familiar to you guys? Well, notice they're dividing by delta s. You see that? Because what is that? It does look familiar. It should look familiar, yeah. I remember in Calc 1, I had a really good Calc 1 teacher that showed me this. Except that we didn't used to write t's and s's. We used to write f of x plus h, we used to write, minus what? F of x all over. Well, now I'm just using delta s, and this was called the difference quotient, or the average rate of change. But if I wanted a derivative, all I had to do was take the limit as what happens? Almost. As delta s goes to 0, that's right. Take the limit as delta s goes to 0, and we will call this thing the curvature. It's a function of s. K of s is my curvature. So it really is talking about the rate of change between blue vector and green vector, right? See, if it were really curvy, let me go to the part where it's really curvy. You know, here's blue, and because it's really curvy, green is like this for the same amount of delta s. And so you might say that pink will end up being a little bigger there. The curvature is bigger there than it is somewhere else. So one way to think of curvature is to think of it as a derivative with respect to arc length. Okay? And as a matter of fact, here's our definition now. Because the other thing you might remember is it gets really annoying to work with difference quotients, and so you all look for much nicer shortcuts. We do that right away in Calc 1. So here's your definition of curvature, guys. Okay? And I'll write that over here. It's dt ds, but then it's the magnitude of that. Okay? So K of s is a scalar. Okay? It's a scalar. It's the magnitude dt ds. So I guess because I want curvature to be a scalar, I should really put this in absolute value bars to be correct. I want a number that tells me how curvy is this thing. Okay? And then the book goes through some really nice examples, which I don't have to reproduce, because if you do the checkpoint exercises, you're going to do some of this. Example 1. Lines have 0 curvature. Oh, I like that, right? I don't want a line to have curvature. Circles have constant curvature. That's nice also. Matter of fact, what is the curvature of a circle of radius r? Well, they show here that it's going to be 1 over r. So k is the reciprocal of, and if you think about it, let me draw a couple of circles for you and just kind of think about this here. So, I don't know, here's my coordinate plane. And let's draw a couple of circles and talk about what's happening. So, you know, let's suppose that each one of these is a unit. Wow, computer's on the fritz today, huh? All right. So, you know, at a particular point, again, if I draw blue, and then if later I draw green, okay, there's a slight change, right? So this circle has a certain curvature. But now let me draw a circle of radius 5. Right? And what you might notice is if I, have again a blue tangent line, and if I move the same amount, you're going to notice that the angle didn't change as much as it does for a smaller circle. Do you see that? So, if this curvature, if we believe that this is 1/2, and then this curvature would be 1/5 because it's radius 5, these are believable formulas at that point, right? And if you get a really small circle, right, take the reciprocal of a small fraction, it's very much changing so that you have this curvature. But for curvature to be defined, you actually have to define a movement. The particle should be moving if we're going to talk about curvature. Okay? And of course, everything I'm doing here, I could just be doing on the plane. Now, it's funny because the definition requires this, but this is hard to use because most of the curves that I'm given don't have S as the parameter. I'm going to give you guys some curve R of t, right? And I'm going to say find the curvature. Matter of fact, look at the homework here. So let's go to the homework problems. Zip ahead. Oh, well, yeah, quick check 1. You guys had to do this, right? The curvature of that circle. Should I do that one or jump ahead to these? Jump ahead? So look here. Basic skills, guys. Find the unit tangent vector and then the curvature for the following parametrized curves. What do you want to see? 16 has a log, 18 has trig. Any takers? Pick one, Paul. 18? All right, so we have cosine cubed and sine cubed. This one happens to be in the plane, right? So this is just 2 space. So really, it's kind of nice. R of t is cosine cubed t sine cubed t. And I want to go ahead and find the unit tangent vector t and also the curvature. So to do any of these problems, you need a formula because that TDS thing isn't going to help. So here's my formula. So I'm going to use the fact that curvature is equal to 1/v times dt dt. So here I go. Curvature is 1 over the speed times dv dt. Well, no, dt dt, sorry. And again, this is a scalar I'm computing. Better write that a little better so we don't get confused. Over v times dt dt, because this is something I can actually compute. All right? So you notice the directions. The directions said first, compute the unit tangent vector. Okay, so let's do that. How do I do that? I guess the very first thing I do is I compute what? R prime of t. Oh, I'm going to need some rules here, guys. Chain rule, right? Like just taking the derivative of cosine cubed, you get bing, bing, times bong. What's the derivative of cosine would be? Negative sine of t. So there's the first coordinate. Right? See if you could do the second coordinate real quick. Sine squared t, because I lower the exponent 1, times what? Times cosine of t. So there's r prime. I guess if I were to simplify it, I would say it's, you know, negative 3 sine of t cosine squared t, comma, 3 sine squared t cosine t. So there's r prime. Okay. And maybe what I want next, because if I want to compute the unit tangent vector, to make it a unit vector, we're going to take r prime of t and we're going to divide by the magnitude of r prime of t. Correct? So let's do that next. Let's compute the magnitude of this vector. So let's see if I can. Let's see. Magnitude of r prime of t would be, well, it's the square root of all these things squared. Something squared plus something squared, right? So let me square the x-coordinate. And I get 9 sine squared t cosine to the 4th power of t, right? Plus 9 sine to the 4th power of t cosine squared t. Okay? And so what you want to do here is you want to take out your common factors, right? So I'm going to factor out the square root of 9 times this stuff. What else is common? Yeah, I have a sine squared and a cosine squared, so I'm going to factor those out. Sine squared t, cosine squared t. I'll leave them under a separate radical. And if I do that, I see what I'm left with. Let's see. Yeah, I guess, well, here I'm left with cosine squared of t plus sine squared of t, but the cosine squared plus sine squared, of course, is equal to 1. So that's kind of nice that that's 1, this piece here. And, of course, that's a 3. And when I take the square root of sine squared cosine squared, what do I get? Yeah, except that you have to make sure, because you're taking a square root, you have to make sure everything's positive. So let's put an absolute value here. Sine of t cosine of t. And so there is the r prime of t. And so I guess I'm going to go to the next page to continue the problem. But I think at this point you guys will be happy saying that my unit tangent vector, so let me copy it down, capital T of t is, well, we have something over 3 times the absolute value of sine t cosine t, and the something was this vector, negative 3 sine t cosine squared t, comma, 3 sine squared t cosine t, right? And of course now what you could do, I guess, is you could factor out your 3's, because it's just a 3 times this vector, and then the 3's are going to cancel. So I could say it's, you know, something like this. 1 over sine t cosine t, and all this is an absolute value, times the vector without the 3's, it would be negative sine t cosine squared t, comma, sine squared t cosine t. Oh, it's getting ugly, but it's there. Okay. So that's my unit tangent vector. All right? The other thing they asked me to compute is the curvature. Question? Kathy, question? Well, let's do it. Let's take this scalar and bring it in so that the sines and cosines cancel. And now I get negative cosine of t, comma, and then I get positive sine of t. So, for one thing, that's a much nicer formula to work with, right? So there's t of t. So now I want to compute the curvature. I'm going to use this formula, 1 over v times dt dt. Okay? Let me write that down. 1 over the speed, this is absolutely crazy, times dt dt, the magnitude of that. So I have a few things here to compute. All right? Let me do them kind of one at a time. Dt dt, let me do this in blue. Okay? I'll do that here. Dt dt, I take the derivative of this and I get derivative of negative cosine would be positive sine of t, and the derivative of sine would be cosine of t, right? And now, since I want the magnitude of that, let's see, well that's the square root of what? Yeah, because it's sine squared t plus cosine squared t. So this is a really nice problem we picked out to do. This whole thing becomes a 1. And so now what I really need to do here is I just need to say that the curvature is 1 over the magnitude of v, and v stands for what? The velocity, right? The velocity vector, which is the same as 1 over the magnitude of r prime of t, right? Which I think we have on the previous screen, right? Because r prime was one of the first things we computed when we wanted to get t, right? We did r prime, we even did the magnitude, right? Yeah, it's this. 3 times the absolute value of sine t cosine t. And so I guess what I need is well, 1 over that, right? So my curvature is 1 over 3 times the absolute value of sine of t cosine of t. All right? So it's going to, the curvature for this curve will be changing as time goes by. All right? And, but that's what I'm getting so far. Yeah, so that looks good. Any questions on that? So, you know, it's interesting because if I just send you home and say, do the homework, this is the kind of exercise you'll do, something like 18, all right? And as you go through section by section, it doesn't get much more challenging. It just, you keep coming across new formulas, all right? So let me show you, for example, this one. Let's go back to the homework. Okay, new section. Alternative curvature formula. Use the alternative curvature formula. K equals magnitude of v cross A divided by v cubed. Magnitude of v cubed to find the curvature. Okay, you can use a formula, I can use a formula, and that's good practice, using formulas. It's not good practice doing calculus. So I think I only assigned one of these. But what I do think is worth doing is understanding where did that formula come from? K equals magnitude of a cross product divided by v cubed. I mean, it's really cool that your book puts that in here. They do it here. An alternative curvature formula. You guys, I was looking through this in preparation for the class, and coming up with that formula, this is a worthwhile exercise. And depending what you want to do, I may spend time after break walking you through this argument because I feel like that's where there's a lot of learning that can take place about vectors. So one problem I have after break might be taking you through this argument. Second problem I have after break. Real live math research. I remember being so excited. This was my second year, or no, third year, well no, second year into my PhD program, all right? And I, you know, I had gotten a bachelor's degree in mathematics, a master's degree in mathematics, but if somebody asked me, hey, what are you going to do for your PhD? Like, what are some unsolved math problems that you're interested in? I couldn't name one. I realized I'd gone through all this math education, but my instructors never showed me, oh, here's some cool problems to work on. And part of the reason is a lot of unsolved math problems, you have to take a whole lot of math before you can even understand what the question is, which is kind of sad. And I'll show you this picture here. I brought in the journal. This is the American Mathematical Monthly that I'm so grateful to Case because they bought subscriptions to all the graduate students to this magazine. And so we were student members, and I've continued to be a member while I'm here at Lakeland because this is a way that you can be abreast of what people are studying in mathematics. Mathematics is still being developed, even though, wow, the calculus I'm learning was done hundreds of years ago. Right? And did you notice yet where I'm pointing? Page 890? Extreme curvature of polynomials. So these two, Stephanie Edwards and Russell Gordon, published in 2004. All right, so now we're 12 years old, but that's not bad, guys. Okay? Results on curvature. Basically, and I have the article maybe here, will be a little bit easier for us to look at. The article is this. Suppose you have a polynomial f. You can compute its curvature using another formula in our book, which I'll show you after break. Actually, there it is. F double prime, 1 plus f prime squared to the 3/2 power. Okay, fine. Here's their conjecture. If you have a polynomial of degree n, the curvature has at most n minus 1 extreme points. What do they mean by that? I'll show you what they mean by that, because you saw a diagram in your book when I was trying to show you guys curvature. See on the right, they're showing you maximum curvature at some place. You see that? Well, if you have a cubic polynomial, I guess what would this conjecture say is that there are at most 2 places that you have maximum curvature happening, right? And so if I draw a cubic, which you guys know how to do, right? There's a cubic, maybe. Where is it the most curvy? Here and here. Maybe those spots are maximum curvature. So these guys had to prove that, or wanted to prove that, and they did. But then they had another conjecture. Maybe you can say something about things that are not polynomials. So I remember my advisor saying, hey, Paul, this is something we might be able to work on. All right? I did not go the differential geometry route. I ended up doing linear algebra. But I still love coming back to this because I've had students, you guys know how there's a project requirement? I've had students read the article and kind of get into it as their project. And I have no idea if that would interest any of you this semester. But I think it is interesting to know that new mathematics is still being developed, and you're at a point now where you can start to understand those questions. So, well, we're at 11:04. I'm going to put us on our 10-minute break. If you guys, so yeah, okay, so where does this formula come from? Well, let's work through a few details. This is where, when I read a math book, I have paper here on the side. I have my pencil in hand, they say. Here I go. I'm going to try and help you through. So, okay. They're doing R of t is x, y, z. And these are all the same old variables that I've been using. But, okay, here we go. It says, and I'm looking at the word because in the first paragraph. It says because vector t, the unit tangent vector, is vector v over magnitude of v. Do you guys get this? That's because what's v? That's r prime, right? And we divide by the magnitude of r prime. So when you think about, hey guys, if you have to compute the unit tangent vector, this is probably how you do it, right? But what we're going to do instead is we're going to talk about curvature here I mean, eventually, so remember, in my mind, I know that curvature is somehow the magnitude of dt ds, right? So I want to use that, and so I'm going to express tangent vector in terms of velocity and acceleration. And so if we multiply both sides by the magnitude of v, I get v here, and I get the magnitude of v, or my speed, times t, right? So that's just taking this equation, multiplying both sides. And now, what I want to do next is I want to get acceleration, a. Acceleration is the derivative of this. But when I'm going to take the derivative of this, it's a product, right? So what do we need? Well, we need a product rule, yeah? And so they say it's the derivative of the speed, that's my u prime v, so times the unit tangent vector, plus, maybe I'll write it like that, and then I have the speed back times the derivative of the tangent vector. Wow, that's kind of cool. So that's their equation 1. Next they say we form V cross A. Wow, okay, how am I going to do that? Well, they say, look, we have a way of writing V, which I just circled. If I move this over, you can see it. And we have a way of writing A, and so let's cross them. And now, you'll notice that this is a sum. And so they're going to do a distributive property. And so when they distribute that VT circle thing over here and here, what do we get? We get magnitude of VT cross derivative of V, well, derivative of the magnitude of V, T, plus, and then we get magnitude of V, T, cross, and then here I get this thing. This is magnitude of V, dt, dt. And you'll notice in the book, the very next thing that they say is, look at this cross product here, and this mess, they say equals 0. Now, why is that? Well, here's a tangent vector, right? What's this in front of it? Because there's absolute values in front of it, that's a scalar. Yeah? Here's a unit tangent vector. What's in front of it? Well, it's the derivative of a scalar, so it's a scalar, right? So think of it this way. We're taking the cross product of two vectors. And by the way, cross product is only defined in R3, really. If you try to define it in some other number of dimensions, how do you even do it? But in R3, what I do is I take my vector, suppose it's 1, 2, 3, and I take a determinant with I, J, K, 1, 2, 3, and then you take the other vector. Now, what's the other vector? I don't know. Suppose the other vector is 2, 4, 6, or something like that. Now, is that really what it is? No. But if you think about when you take this cross product, what would happen? Well, you look at I, and so you look at what's the determinant of this matrix. 12 minus 12, you get 0. See, if you take a cross product of two vectors that are basically scalar multiples of each other, you get the 0 vector. If you take the cross product of parallel vectors, you get the 0 vector. as your vectors get more and more angle, that increases the size of the cross product vector. So what's really cool is that if you look at what I just did, I did V cross A, and a lot of it went away. All I have is this stuff up above here. This VT cross magnitude of V dt dt. So I guess I could say it's just this. And so now, what they're going to do is they're going to say, well, let's think about the magnitude of that vector. So the magnitude of this vector equals the magnitude of that stuff. And that's kind of this argument going on here. But I do have to watch my time, how much more to do. Yeah, so rather than do any more with that formula, I want to move on to a little bit of this and probably do a sample problem for you. Engineers like to do this. They like to say, okay, let's talk about the acceleration. Let's talk about the tangential and normal components of acceleration, all right? So the picture is, or the equation is there in the box of theorem 13.13. Really lucky theorem to be talking about here. A, that acceleration vector, you can break into the piece that goes along n plus the piece that goes along t. And so you'll notice that they're going to write an, that's a scalar, and they're going to write at, that's another scalar. You guys, back in physics class, when I first learned physics, I remember first studying vectors, and we would break them into the x component and the y component. And what you did was you studied everything in terms of x and everything in terms of y, and then put it all back together. That's how physics, high school physics worked, right? Well, you play the same game when you're traveling on curves through space, but the x and y that you use are the tangential and normal components, right? So again, see this green vector? They're saying that's my acceleration. And I know that the pink and the blue are perpendicular to each other. So what I can do is I can say, well, I can project. Now, let me show you this. Right? So for any particular place, you tell me when to stop, doesn't really matter, I guess. There, we can see everything pretty well there, right? Green is the acceleration vector. Right? Now, by the way, how do I know that this picture, these are, the blue one and the pink one, those are not t and n? Because the length is changing, right? If they were t and n, the length would both have to be 1. What we're doing here is we are projecting. We're taking this here, right? What we're doing is when we say a sub n times n, it's a scalar times n. So, you know, the picture is maybe, hey, n is a unit vector, but a sub n times n, maybe it's longer, right? So in my picture there, it's, you know, actually longer, but in the same direction. And maybe pink is short, right? The tangential component, it looks to me like, is short. But the point is that it has to be perpendicular. And so they give you, again, some formulas for computing these things. I don't think you'll find them terribly difficult. It's just follow examples. But we'll see. We'll see. But I am going to go to the end of the homework where they start talking about these maximum curvature examples. I really like some of these. Special formula, curvature for plane curves. show that the curve given by f of t, g of t, has this as its curvature, where all curvatures, all derivatives are taken with respect to t. And then we're going to use this formula to find the curvature of some different curves. So, let me think what to do next. Let's try to make use of this formula in the following way. So I'm going to write down that formula and then see if I can use it. K of t is equal to magnitude of f prime g double prime minus f double prime g prime, that magnitude, over magnitude of, or no, it's, yeah, f prime squared plus g prime squared in the denominator. And then, oh no, they don't say magnitude. What they do is they say I'm taking this mess to the 3/2 power. All right, so how am I going to use that for you guys? They suggest trying a circle, an ellipse, an asteroid, parabola. Well, I really like the idea of a parabola. Matter of fact, let me do a polynomial in general. Okay. So suppose y equals f of x is a polynomial. All right. Now, if that's true, so example would be, you know, y equals x squared, or y equals x cubed, or 3x cubed, or whatever, right? You can make up whatever example you want for a polynomial. And I want to talk about the curvature just of polynomials, let's say. Okay? Well, the problem is this formula only works in the situation where you have it written like this, r of t, right? And they say it's a vector, and so it's given by f of t and g of t, right? So how do you fit formulas like this into the world of polynomials? Well, the answer is you just have to think about how to parameterize it. So I'm going to do this. I'm going to say, let's let t equal x. Okay? No. That's even better. F of t is x. Oh, but this is confusing. This is confusing. Sorry, guys. Too many f's. We don't want a lot of f's in Calc 3, right? Here, let me put this, let me make that a big F, and let's hope this is the only big F we're going to have to write this year. All right, so there it is. Big F of x is my polynomial. So maybe big F of x is 3x cubed. I don't know. All right, so here I go. So r of t is going to be, if little f of t is what I call x, then g of t is what I'm going to call big F of x, right? Cool. So here I go. I'm going to use the curvature formula up above. Let's see what happens. Curvature is given by, well, that formula says it's a magnitude of something divided by something to the 3/2 power. That's okay? Now where it says f prime, remember little f of t was x. So let me kind of continue there. F prime of t must be equal to 1, right? And f double prime of t exists, but it equals 0, right? Okay, fine. And then this g of t is what I called big F of x. So g prime of t is big F prime of x, and g double prime of t is actually just going to be big F double prime. Alright, so here I go. Almost done, which is good because I think I'm at 1150. F prime g double prime would be 1 times this. So this is F double prime minus what? 0, because F double prime is 0, all over, what's F prime squared? 1. Now we're freezing, aren't we? And then g prime squared would be this F prime squared. We are completely frozen. It's time to send you home because, actually look, if you look at what we just derived, that's the formula right here. F double prime plus 1 plus F prime squared to the 3/2. Alright, you guys, drive safe today. Hi everyone. This is an addendum to problem 18, which we were working on in class, and you may remember I paused when we got to the second part of it, and we wanted to do what the solution manual did and distribute this scalar, and I said, I don't know if I like that move. And so we did it. We found a simpler version of the unit tangent vector, but it ends up being incorrect. Although it's a nice way to then compute the curvature, which if you say that's the overall goal is to find the curvature, then it works just fine. Let me show you why that is on the calculator if I can. So if we go back to this expression here that we were working on, the original problem was cosine cubed t and sine cubed t. So I'm going to take out my graphing calculator, and in order to graph this, I'm going to change the mode to parametric mode, which allows me to plot graphs on the plane with parameters. So when I hit the y equals screen now, it's going to ask me for x and y. So I'm going to open parentheses, type in cosine of t cubed, and I actually don't even need parentheses when I think about this. The y coordinate is sine of t, close parentheses, cubed. And now if I sketch a graph of this, what I'm going to do is I'm going to try and pause it as it moves. Now, it's a little too small to see, so we're going to zoom in here. And I can hit enter while it's graphing, it'll pause. Well, okay, it's a little bit quick. We'll try one more time. There, that's what I wanted to do. You'll notice that t starts at 0. So for example now, if we look at the table, it's not doing it right now, but t starts at 0 and advances to 2 pi. And as it does, this is a bit like a polar graph, right? You can see that my function starts out when t is 0. The cosine, of course, is 1, and the sine is 0. So we're at the point 1 comma 0. We move to 0 comma 1. We're going to move to negative 1, 0. But maybe the interesting thing to ask is, what's true about the unit tangent vector? And I guess it depends which form you use. If t is 3 pi over 4, the cosine of 3 pi over 4 is negative radical 2 over 2. So this x-coordinate is going to be positive radical 2 over 2. And the sine of 3 pi over 4 is also positive radical 2 over 2. However, if I plug in 3 pi over 4 into this expression, well, of course, this fraction will be a positive number because I have absolute value bars down here. And the first coordinate would be negative, and the sine of 3 pi over 4 we said is positive, and cosine squared is also positive, so that gives me a negative x-coordinate instead of a positive x-coordinate. And you can check that if you plug 3 pi over 4 in for the y-coordinate with the sine squared cosine, you're going to find that you get a negative y coordinate rather than a positive y coordinate. So, in some ways, the tangent vector is pointed in the wrong direction, where instead of being positive positive, it'll actually be pointed negative negative. Now, both of those seem to be understandable. I mean, it's along this line. In any case, it's going to give you the correct tangent line and the correct curvature, but not the correct orientation along the curve. And so, yeah, that's why I was hesitating here. I hope that makes sense to you. But in terms of curvature, it just didn't matter. Little subtleties like this are quite interesting.